The next concentration inequality is Hoeffding's inequality. This is very important. So the Hoeffding's inequality proof based on Hoeffding's lemma. When we have bounded random variable, so the range of random variable x is from a to b, then for all positive theta, the MGF function, the MGF value is bounded by exponential theta square b minus a square over 8. So this is Hoeffding's lemma. And using this Hoeffding's lemma, we can derive Hoeffding's inequality, which is let x1 through xn be independent random variables when xi is bounded by ai to bi. So each random variable is bounded random variable from ai to bi. Then the concentration inequality, the concentration probability, the sum, the empirical average of xi minus expectation of xi. So from the law of rising number, we know that the summation of xi times 1 over n, the empirical average, will converge to the true average as n go to infinity. But for finite n, we don't know anything yet. And the Hoeffding's theorem inequality tells us the convergence speed to the true expectation and deviate from the expectation as much as t, which is essentially less than or equal to exponential minus 2 times n squared times t squared over summation I1 to n bi minus ai squared. So this is very nice result because as n goes to infinity, as n grows the exponential, the inside of exponential function, this value very rapidly go to negative infinity, which means this probability converts to 0 very fastly with respect to the number of sample n and the error t. Okay, the Hoeffding's lemma tells us very nice property of concentration, especially when its random variable is bounded by some constant. Okay. So this is the proof of Hoeffding's lemma. So let y is equal to x minus expectation of xi, so that y is a zero mean random variable. Then since y is in between a prime and b prime, here a prime is a minus expectation x, b prime is b minus expectation x, then y minus b prime plus a prime over 2, the absolute value of this is bounded by b minus a over 2 because of this bounded range. Therefore, we have this. The variance of y is equal to variance of y minus some constant. So when you add or subtract some constant, the variance never changes. And which is upper bounded by the expectation of just the square of random variable, y minus b prime plus a prime over 2. And since we know that this absolute value always bounded by b minus a over 2, the square value always less than or equal to b minus a square over 4. Okay, so this is very basic property. So now let's introduce very clever idea, interesting trick. Let's define psi function like this. Psi y of theta is equal to log expectation of e to the theta y. So since y is bounded random variable, the derivative of psi y theta is well defined as follows. From this log property, the expectation of theta e theta y go to denominator. In numerator, we have expectation of y e to the zeta y because the derivative of e to the zeta y is equal to y times e to the zeta y. Okay, this is the first derivative of a psi y function. Using this psi y, we can define a new probability measure q as follows. So this is a probability measure we can easily check. From the definition of psi y, we know that expectation of e to the minus psi y zeta. So what is this? This is equal to 1 over expectation of e to the zeta y. So from that, when you take the entire set here, we can easily check this is equal to 1. And also we can easily check that this is always non-negative. So the QA value with any event A, the value is always non-negative. And also the Q value of the entire set, Q function of entire, Q measure of entire event set is equal to 1. We can easily check that. So Q is also a probability measure. So let's denote by EQ and bar Q, the expectation and the variance with respect to Q. Then the second order derivative of psi y zeta is from the chain rule. We can easily derive this second order derivative and just move this to here using the psi y zeta notation. We have this equation, and from the Q probability measure, the new probability measure, very interesting. We here both term have this, so we can rewrite the previous line by this. And very interestingly, this is exactly the variance of y with respect to the measure q. And also we know that with any probability measure, because y is bounded and the y minus a prime plus b prime over 2, the absolute value is always bounded by b minus a over 2. We know that the variance always less than or equal to b minus a square over 4 with any probability measure q. So we have this final inequality. And since pi y 0 is equal to 0 and pi y, the first derivative 0 is also equal to 0, since we define y so that y expectation equal to 0. From Taylor's expectation, we know that there exists psi such that psi y zeta is equal to 1 over 2 the second order derivative of pi y psi times zeta squared. And from this, we know that the second derivative of pi y always upper bounded by b minus a squared over 4. Finally, we have this. This is Hoeffding's lemma. So now using Hoeffding's lemma, let's show Hoeffding's inequality. From the Markov inequality and MGF, we have the first inequality line. And from the Hoeffding's lemma, we have this. Nothing difficult. From MGF and Markov inequality, we have this as the Chernoff bound. And from the Hoeffding's lemma, we have this. Now let's optimize this term, because as we did in Chernoff bound, we can insert infimum over all zeta. So let's optimize this term by controlling zeta. Then the solution of zeta is equal to 4 times nt over summation of bi minus ai squared. So using this zeta, we have this concentration inequality. Right. So this is very, very nice property. Although this also, the denominator also increases as n go to infinity. So the increasing speed of the denominator is just linearly to n. But the numerator we have n squared. So from that we know that the exponential minus n times some constant means the concentration inequality go to zero very fastly, exponentially fast as n go to infinity. That is very nice concentration behavior. Okay.